I will discuss the new progresses that we have obtained on the tidal dissipation, both in stars and in planetary fluid layers. So this is a work that has been done in collaboration with my two PhD students, Pierre-Auclair Desretours, Mathieu Huenel, and the colleagues in celestial mechanics, Christophe Lepont-Saint-Lafitte from Paris Observatory. So just to begin with a general context that has been already highly detailed by Celia, we are in the space photometry revolution, and thanks to this revolution, we are now able to characterize at the same time new planetary systems and also to characterize, thanks to asteroseismology, their host star, and thus to have some information on their structure, and we will see that it's very important for what is related to tidal dissipation in stars. And we get some information, of course, on the orbital architecture. Here you have a system, which is a Kepler 11.1, where you have, for example, 6 planets of super-Earth and Neptune-sized planets, among which 5 of them are in an orbit which has the size of the one of Mercury. So we see that we have amazing orbital architecture to explain. On the other side, thanks to seismology, we are now also able to constrain the relative inclination between the spin of the star on the orbital plane. And thus we have to explain both the spin and the orbital evolution. And to do so, we have to understand the angular momentum exchanges. And one type of interaction that has been presented before is a tidal interaction. So this is a theoretical picture of the present state of the art with which we have to deal with. You get a system with a given orbital architecture, and depending on the size of the orbit, we have a different tidal interaction with different strengths. As in the Earth-Moon system, we are living in a binary system, as this has been emphasized this morning. You will be able to generate velocity field inside the body. For example, if you look at the oceanic shell in the Earth, we have the tidal interaction we can see every 6 hours. But of course, each body, both stars and planetary interiors, are dissipative. And because of this dissipation acting on the kinetic energy, we will be able to transfer angular momentum from the orbit to the spin of the body or vice versa. And this is described by the tidal quality factor, the Q factor, which scales as the inverse of the dissipation. So as in a forced oscillator, if you have a high quality factor, that means that the dissipation is weak. If you have a small quality factor, that means that the dissipation is high. And thus we have to understand, in fact, the link, as this has been emphasized by Isabelle Baraf, between the tidal dissipation and the structure of the planet. Look at the Earth as an exoplanet. If I look at the Earth as a very distant planet, it's a rocky planet. And thus, I can say the tidal dissipation will be the one of rocky layers. But in fact, if you look at the constraint we get from the satellite to look at the tidal dissipation on the Earth, you see that you have a dissipation which is higher of 1 order of magnitude compared to what is predicted for rocky layers. And the fact is that, in fact, you have the thin oceanic shell, and this is this fluid layer which acts to dissipate mainly the moon gravitational energy, which is pushed to the tidal displacement. And this shows the importance to have very precise structure model. So now, what happened in fluid planetary layer and in stars? This is a diagram which will be very familiar to asteroseismologists, of course, because in fact, what you will do is that you will excite the waves in fluid, not thanks to stochastic excitation or to the kappa mechanisms, but because of tidal interaction. And you will have the same type of wave which are observed by seismology. The gravity waves, for example, in the stably stratified layer as the radiative core of the Sun, or the external small radiative envelope of Jupiter, or the terrestrial atmosphere. This is driven by the Archimedean force. You will have the Coriolis acceleration, which will drive some waves, which are the inertial waves, also called the Rossby waves in atmospheric physics. And because you are at low frequency, you can have mixed mode, both gravity and inertial at the same time. So they are gravito-inertial modes, and they are all excited by the excitation, by the tidal potential. What is the source of the dissipation? In a highly turbulent convective motion, it will be due to the turbulent friction that is applied on tidal displacement, and you will have also thermal diffusion, and in stable layer, this is the diffusion of heat, which will dissipate the gravity waves. So what is amazing with that is that you have a forced oscillator, and thus you get a highly resonant erratic tidal dissipation spectrum. Here you can see the dissipation spectrum by turbulent friction in a convective envelope of a Jupiter-like planet as a function of the tidal frequency, which gives you the relative degree of asynchronism in the system. And you see a highly erratic spectrum, so this is the dissipation, and you see that it's very, very strongly with the tidal frequency. So, do we have to take into account such complex behavior when we look at the tidal interaction and tidal evolution? I will look at the simplest system as possible, a coplanar system with a circular orbit with non-synchronized body to look at the effect of such dissipation. First, look at the case of two rocky bodies, the Mars-Phobos system. Here, we will have a smooth dissipation as a function of the tidal frequency, and you can see here you have the spiraling of Phobos to Mars planet, and you can see that depending on the power that you get from laboratory experiment for rocky layers, that you will have a smooth evolution of the satellite to the planet. But you see that you have a link to the rheology of this fall onto the central planet. So just replace Mars by a fully convective body of the same mass of Mars to see the difference. Here I show you the tidal dissipation spectrum as a function of the tidal frequency, and you see that it becomes highly complex. And here now, you can see in green the evolution because of this highly complex resonant dissipation compared to the classical model, and you see that you have a highly different evolution with some steps which are due to when you pass through a resonance. And in fact, the semi-major axis jump is directly proportional to the width of the resonant peak and to the height of a resonant peak. And so we have to characterize this spectrum to be able to give to celestial mechanics bodies or to observe what happened with such erratic tidal dissipation. And to do so, we choose to adopt a reduced local model where you put a box inside a star or a planet. You look at Cartesian geometry, which is inclined. You have possible stable stratification, and you have both viscous and thermal dissipation, and this is a generalization of the work by Gordon. And here you have some parameter of control, which is the ratio between stratification and Coriolis acceleration, and the viscosity compared to the rotation, and the same for thermal diffusivity. This is a spectrum you get, and what we have to understand is the frequency range which is excited, the non-resonant background, which is also called the equilibrium tide, and the resonance properties, for example, the number of peaks, their height, and their width. This is for inertial waves in a purely convective region. So this is an evolving behavior. Here you have different spectrum. If I decrease the viscosity for a fixed rotation, or if I increase the rotation for a fixed viscosity, and you see that going that, I increase the number of peaks and their height. And also I can increase the stratification to go in the solar type star radiative core, and you see that I modify the frequency range of tidal oscillation. Can we give some clues on that? Yes, in fact, we are able to isolate four main regimes. The first one is the one which corresponds to inertial waves in convection zone, and depending on the strength of turbulent friction and heat diffusion, you are able to say where you are in this diagram. If you go to stable layer and the Earth's atmosphere or the stable radiative core of the solar type star, you will have gravito-inertial waves which are mostly dissipated thanks to the diffusion of heat. And what is very interesting with this reduced model is that we have been able to characterize completely analytically both the width of the peak, the height of the peak, which are the input you need for the orbital evolution, also the background, and what is tricky because before we have simulation and we see a lot of peak. When I decrease the viscosity, here we are able to predict the number of peaks as a function of viscosity, rotation, and whatever you want in this reduced model. So here we have some scaling laws that we can include in celestial mechanics equation, and this asymptotic law, which depends, for example, here you have the width, it depends on the viscosity or the thermal diffusion, depending on which side of the diagram you are. You can include it in your celestial mechanics code, and we have been able to compare our asymptotic regime to the complete numerical modeling, and it matches well. But this is only local model, and we have to go beyond this picture because, of course, we have to look at large scales both for stars and planets. And in planets, it's particularly difficult because you have to manage both fluid layer and solid layer at the same time. So, as emphasized by Isabelle Baraf, we need more and more refined model of internal structure with more and more realistic equation of state to know if we deal with convective layer, stably stratified layer, if the central core, for example, of giant planets are solid or liquid, and such type of thing. And with that, we'll be able to deal with the complex internal structure and rotation and see how they impact the tidal dissipation. And thus, we need an ab initio physical modeling. And thus, here I will present the last result we get with Mathieu Guenel, who is in the room. This is the poster number 97, and where we did a frequency average model to predict what is, in fact, in each type of layer, the reservoir of dissipation we have inside a planet. Here I take the case of a Saturn-like planet because we have to use the synergies between exoplanet and solar system physics. And in Saturn, we have been also able to measure the dissipation rate for the moon at different tidal frequency. Here you have a scheme, a cartoon, which gives you the structure. You have a deep convective envelope, and you have a possible rocky core. And what we have done is that to look at the different reservoirs of dissipation in both the rocky core, if it exists, of course, and in the large convective envelope. And thanks to results obtained for fluid layer by Gordon Ogilvy and by Françoise Remus and collaborators for the anelastic dissipation, we have been able to compare the different strengths, the relative strengths of the tidal dissipation as a function of the ratio between the radius of the core and the total radius of the planet. And here you can see an average over the tidal frequency of the dissipation. In red, you have the anelastic dissipation, and in blue, you have the dissipation for different rigidity of the core, and in blue, you have the inertial dissipation for different velocity. And you see that it evolves, of course, but what is very interesting is that before we are doing some free dissipation without taking into account the core, and other thing where we are doing the anelastic region but ignoring the inertial wave, and you see that both can compete and that both must be taken into account in the same time. What is interesting with this new approach, designed originally by Gordon Ogilvy for fluid layers, is that this gives you the possibility to make frequency average grid of tidal dissipation as a function of stellar and planetary type, and to compare them directly to the observation obtained by high-resolution photometry mission. And so the perspective is that we have shown that now we have to go beyond the usual models that are assumed for tidal dissipation, because we are able now to manage resonant tidal fluid dissipation. We have also able to look at their dependence on the rotation, stratification, and so on, so the internal structure. We need global models. This is developed in collaboration with Clément Baruto, Michel Riotor, and people around Gordon Ogilvy. And we need also to characterize the much complex case where you have a layer, stratified layer, in a big convective layer, as in the case of stratified convection, as proposed by Gilles Chabrier and Jérémy Lecomte. And of course, I cannot ignore the magnetic field because Jan is in the room and he will point to me that stars are magnetic, and thus we have to take into account, of course, magnetic field, both in stars and planets, to make a definitive link between spin-orbit evolution, tidal dissipation, and the internal structure of star and planet. And I thank you for your attention. And I just point that I'm the responsible of the star-planet interaction work package for the Plateau mission. So if you are interested both on the theoretical effort or observational constraint, please contact me. And I thank you.
Thank you, Stéphane. Ian. Right, okay. Here.
Yes, I'd like to come back to the inertial wave dissipation. And so you showing the results as a function of core mass. I believe Jeremy Goodman also had shown that you have this very strong dependency with the with the core size to the fourth power or something like
exactly.
That. How does this change if you change the interface so that we can imagine that the core is not well defined, but is partially mixed, as you mentioned, with double diffusion, maybe between the core and the envelope.
Okay, so two cases. First, imagine that we have the large-scale envelope of hydrogen and helium, and inside we have a core which is liquid of silicate and things like that. In fact, you have a dependence on the radius, which is represented here, and you see that the inelastic dissipation and the inertial wave are quite the same dependency. But the other very important parameter is the jump of density between both types of regions. This is the other control parameter. For the analytic dissipation, you have the rigidity and the jump between density between the core and the envelope, and this is the same for inertial wave, but this time with the rotation rate linked to the Coriolis acceleration. Also, if you have, as it has been proposed for giant planet, around the core, a stably stratified layer, there you have to take into account the stratification, and we have not yet done the prediction when you take into account for this frequency average model, the stratification, but of course, we can imagine that you will have a dependency on the jump of density, the stratification, and the rotation rate.
Probably you expect smaller dissipation?
I don't think so. In fact, gravity, when you look at the result by Gordon and Douglin for star, you see that when you have stratification, you can increase the rate of dissipation, and this is also shown by our scaling laws in the small box.
In this plot, as you know, the dissipation rate of the core, you cannot calculate from first principle, right? Because it's the rocky dissipation of the rock cannot be predicted. So there are quite a number of free parameters. So what did you use in this plot to make this comparison between the fluid dissipation and the rocky dissipation?
So what has been done in this work from first principle, we calculate self-consistently the tidal displacement in the anelastic region. We take into account the constraint applied by the fluid layers. This has been done in Remus and collaborators. Where I completely agree with you is that what we are choosing for the rheological parameters are the rigidity and the viscosity. In fact, if you look at the frequency average dissipation rate, it does not depend on the viscosity. This is the same as for inertial waves. So you have to choose the rigidity. And what we have done is that we have looked in the literature, what has been done, of course, in the case of the Earth, and you have a paper by CoRoT, which gives you a possible extrapolation to the regime of giant planet, and this is what has been assumed. Of course, now François will do a postdoc with Stéphane Mathis to look at equation of states in giant planet and to derive from first principle simulation of equation of state a good prediction for the rigidity of the core. So I agree with you that the main point is what the coefficient transport, in fact.
Isabel.
Oh. Thank you. Yeah, I fully agree with you. It's very important now to characterize the effect of the stratified convection. But there are two possible scenarios with this double diffusive convection in interior of planets. So either you have layers which form with very thin diffusive layers and sandwich between thicker convective layers, or you may have super adiabatic convection, which means so actually how would this change, for example, in terms of dissipation? Do you think you could find signatures of whether it's real layered convection of a kind or super adiabatic convection, inefficient convection?
In fact, our idea is to take as a first step in the work, is to take the case of when you have a stable layer inside the large convection layer, to put the box, to take the convective box and to put inside the small diffusive layer. And we will be able to calculate the spectrum, and here we will look at if we are able to generalize our scaling laws for purely convective or purely stably stratified to such case. For the super adiabatic convection, I think that using 3D numerical simulation in a small box when you can reach high level of turbulence will be one of the way we can look at.
Okay, thank you.
Let's thank Stéphane for the stimulating paper again. Thank you, Stéphane.